I'm feeling it, feel the glass, you just feeling it, feel the legs pushing up on the set. I'm feeling it, feel the high that you get from the line.
I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course.
Alright, so finally we're going to wrap up this video with the third part, final part, MRI, or magnetic resonance imaging. So the NMR phenomenon was initially discovered and explained by physicists back in the 1950s and 60s. And so around that point, it was a very good analytical tool for chemists. By the early 70s, scientists began realizing that imaging parts of the body using NMR could be a valuable tool as a diagnostic medical technique. However, because the term nuclear magnetic resonance sounds to many people as if the technique might involve radioactive materials, which it doesn't, healthcare professionals started calling the technique MRI, magnetic resonance imaging. Now, this became so important that in 2003, the Nobel Prize for Medicine or Physiology was awarded to Paul Lauterbur and Peter Mansfield for their discovery that led to practical MRI in the medical field. So the basis of this is that spin-excited nuclei relax at a rate that's dependent on their environment. The body contains several nuclei that in principle could be used for MRI. Of these hydrogens, most of which come in the form of hydrogens attached to water molecules, triglycerides, and membrane phospholipids will give the most useful signals. Also, phosphorus MRI can be used sometimes in diagnostic medicine. So remember that in NMR spectroscopy, the energy in the form of the radiofrequency radiation is absorbed by the nuclei in the sample. The relaxation time, so that is the excited spin state relaxation back to the lower spin energy state, is characteristic at which it's at a characteristic time at which the excited nuclei will give up this energy and relax back to that ground state. Now, as that spin state relaxes, the energy has to be released, energy has to be conserved, and so photons are released, photons of electromagnetic radiation that can be picked up by a detector in this imaging technique. Now, the key to any medical imaging technique is to know which part of the body gives rise to which signal. In MRI, spatial information is encoded using magnetic field gradients. So remember that there's a linear relationship between the frequency at which a nucleus resonates and the intensity of the magnetic field. Now, typically in carbon NMR, hydrogen NMR spectroscopy, we use a homogeneous or isotropic magnetic field so that all of the hydrogens will absorb at the same radio frequency and have the same chemical shift. In MRI, this is a bit different. So you're placed in a magnetic field gradient that can be varied from place to place around your body. And so nuclei in the weaker magnetic field gradient are going to absorb at a lower frequency. Nuclei elsewhere in the stronger magnetic field absorb at a higher frequency. And in a magnetic field gradient, there's a correlation between the absorption frequency of the nucleus and its position in space. And so a gradient along a single axis images a plane in your body. And so two mutually perpendicular gradients will image a line segment, and three will image a point. And so eventually you're able to generate an image like that on the right-hand side, corresponding to different slices, essentially, through your body. So the main takeaway from this is basically that MRI, these medical imaging techniques, draw from the same fundamental concepts of NMR. So you're placed in a strong magnetic field. The hydrogen protons attached to the water molecules in your body are going to align either parallel or anti-parallel with that field. And then radio frequency pulses will excite the hydrogen atoms. And when those radio frequency pulses stop, the hydrogen ions are going to return to their native spin state and release that energy as a photon that can be detected. So this is usually really low energy in the picowatt range, but that's detected by the MRI. sent to the computer, and that signal from the protons is transferred or transformed into a spatially encoded image.
Feel the high that you get from the line. If you feel it, raise your hell in the sky.